Welcome everyone, my name is Demian Nahuel Goos. This is the Treachery of Mathematics, the fun of intertwining arts and mathematics for the May month of Mathematics 2020. I'm half German, half Argentinian mathematician, and I find myself at this very moment in the south of Argentina, in the middle of the woods of Patagonia. So we frequently hear that mathematics is always correct, that it is an exact and perfect science. All numbers and equations and geometric shapes. One could argue that it's kind of boring. Always the same formulas we learn at school, right? Well, no, of course not, far from it. Mathematics can actually be fun, sparkling and inspirational. But not only that, there is actually inherent beauty in mathematics, a superior aesthetic, one could argue, art. So today I would like to talk about this. I would like to talk about our understanding of mathematics, about imperfections in mathematics and how these imperfections can actually make mathematics more beautiful, as they surprise us, they take us off guard, and they show us a part of mathematics that we usually don't expect to be there. To do so, I would like to use arts. I would like to share with you a series of artworks I created which actually talk about all this. Once again, welcome everybody, I hope you enjoy it. So, let's start with different artworks in which we can find mathematics. On the left, by Albrecht Dürer, we have Melancholia, an artwork with different geometric shapes, and on top right we even have a magic square. On the right we have Leonardo da Vinci's famous Vitruvian Man, a study of proportions. And if we stay in Italy, we would find that different Renaissance artists like Filippo Brunelleschi or Leon Battista Alberti, they created a whole new branch of mathematics in their search of aesthetic perfection. We now call this branch projective geometry. And if we talk about arts and mathematics, it is impossible not to mention M.C. Escher, probably the most distinguished artist who used mathematics in his work. So this was arts using mathematics. Now we go to mathematics using arts. Here we have different artworks which show mathematical concepts. These are simply different numbers depicted with different shapes. This is a Fourier approximation of a function. And when we talk about arts and mathematics, mathematical concepts depicted with arts, fractals are always very close. So yeah, and now we go to my own artworks. So the whole series is called The Treachery of Mathematics. We have 12 individual artworks, each one of them refers to a different branch of mathematics, like probability, algebra, or topology. And we see in every one of them an everyday object like some glasses or a hat, and behind each and one of them there is a paradox or a counterintuitive result hidden. And the whole artworks, they all together ask the question, is mathematics suitable to describe our reality? So this is because we are always talking about counterintuitive results. Can we trust mathematics to describe our world? So that's the main idea, and it was inspired by two artists. The main one is René Magritte, and the second one is Henri Matisse. Let's talk about them a bit. So let's start with René Magritte. René Magritte was a Belgian artist. He was a surrealist and he created different artworks, paintings, which seem to be familiar when you first see them, but if you observe them more carefully, you will see they make you think. Here are two examples. On the left, this is a statement about human curiosity, the desire of humankind to see behind what we can see, to see behind what we have discovered, and the desire to see beyond. On the right, this is a statement about the human capability of understanding the future. So we are able to project, and if we have an initial setting, to understand what will happen next. And these both statements, they have a mathematical interpretation. If you think about it, it's mathematicians are driven by curiosity, and mathematics, not always, but it's always about projections about what will happen if we have this initial setting. So there is a mathematical interpretation. And then we have rather philosophical questions. On the left, he plays with misunderstandings with language. So if a mermaid is a half a fish and half a woman, then here we see a mermaid. And of course, what he tries to say is, how can we trust language to describe our reality if there is so much room for misunderstandings? On the right, the same question, but with images. So we see a pipe and the statement, this is not a pipe. The answer is, it is not a pipe because it is a depiction of a pipe. And again, how can we trust images to describe, to visualize our world, if there can be so easy misunderstandings that can arise from doing so? Of course, this has to do with his whole work, where he plays with images and perception. And so this question, how can we describe reality with language and with pictures, connects to my question, how can we describe reality with mathematics? And then we have Henri Matisse, a French artist from southern France. And why did I choose him? So there is a reason behind this. He was a very famous artist, and then he had some health issues and he was bound to a wheelchair. And instead of giving up and saying, okay, I can't paint any longer, so I will stop doing this, he created a whole new way of doing art. So he cut paperboard in different colors and made an assistant put them all together and created by this means new ways of doing art. And why I chose this is because the mathematicians who came across all this contradictory results and these paradoxes and so on, instead of giving up, instead of saying, okay, I don't have no idea how to deal with this, they all found new ways to find a solution to these problems. And that's why I connect this idea behind the work of Henri Matisse with my artworks. Because my artworks are actually, again, paperboard in different colors, cut and put them all together. And a funny little detail, when I first submitted my artwork to a conference, a mathematical conference, the review was, I was accepted, it was accepted, but one of the reviewers said, well, this is childish. And of course it is childish. If you see my artworks, they are not that serious. But and it was a little bit mean by the review to say so. However, I was very happy because that's the exact same thing people said about Matisse's work, that it was childish, that it was not serious art. And so I was very happy when they said this, although it was a mean statement about my artwork. So let's get started. We have here different artworks and I will show you some of them and we will talk about them. Let's start with the bottom left. This is the Treachery of Numbers. We see a Nautilus shell and the statement, this is not a number. So we use this Nautilus shell today as a real-life representation of this curve here. This curve is called the golden curve because its growth factor is phi, the golden number, the golden ratio, which we see it here. We know this number is not rational, it is irrational. Why? Because it is not the fraction of two natural numbers. And then we have the statement, this is not a number, and this is a reference to Pythagoras. There is a very famous quote attributed to him which stated, all things are numbers. And what did he mean by that? Well, the whole Pythagorean, the group, they we now consider them to be the first mathematicians. There are two main reasons for this. The first one is they were the first to do pure mathematics. That means with no real applications. They did mathematics for the sake of it, because they wanted to and not because they needed to. And the second one is because they connected mathematics to philosophy. Their whole world view, their philosophy was based on this statement, all things are numbers. So their whole way of understanding the world was based on natural numbers. So let's see an example of what I want to say with this. Let's imagine we have these two lines, A and B, and we want to compare them. So we see B fits 2 times in A, and there will be a small remainder left. We can write A equals 2B plus R, the remainder. And now the remainder is a bit smaller than B, so we can compare them. And once again, the remainder fits 2 times in B, and we have another new remainder. We have another equation we can write, and now we can compare and keep comparing the remainders and keep comparing until there is no remainder left. Here we have R2 equals 3 times R3 with no remainder left, so we cannot keep doing this, yes? So we have now here 4 equations, and if we compare them and combine them, we obtain this equation, 11 times A equals 26 times B. And this is what they mean with all things are numbers. They call this, so we now say A and B are commensurable, and this equation, we have here a natural number and we have here another natural number, and that's what they meant with all things are numbers. So what happened next? They wanted to compare these two lines. This is a pentagon, a very important shape for Pythagoreans because this was the logo of they had, and so the comparison between the side of the pentagon and the diagonal, it was very important to know which relationship was behind that. So they drew different lines. You see these are smaller and smaller stars they drew, and I think you can see that it is possible to draw as many stars inside as you wish. In theory, there are infinitely many stars that can be drawn. So we have a smaller diagonal and a smaller side because we have a smaller pentagon here, and we have even smaller pentagons, and again you see we have infinitely many D's and infinitely many L's. And so if you start comparing them, what do you obtain? Well, D equals L plus D1, the smaller diagonal. Now you compare L to D1 and you obtain that the remainder is L1. And now you have to compare D1 to L1, and if you check this out, you see this is the similar situation to the initial one. You have the diagonal and the side of a smaller pentagon, and so you probably see that you will get into an infinite loop because you will start comparing smaller and smaller quantities, and this will never stop because you will never have a last pentagon in this geometric representation. And so what does it mean? If you have infinitely many equations and you have no last equation with no remainder left, then you cannot combine these formulas just like we did in the first case, and you will have no equation with natural numbers with D and L, just like in the example we gave right now. And this means that D and L are not commensurable. Today we know that if you divide D by L, you obtain the golden number, the number I just mentioned at the beginning of this chapter. And what's the problem? Well, the problem is this contradicts the whole philosophy of the Pythagoreans. So there was one mathematician among the Pythagoreans, Hippasos, what's his name, I recall, and he said we have to share this to the world. This is very important news, we have to share it because we discovered something that we did think is not existent. Pythagoras and the gang, they were not amused. Why? Because this contradicted their whole philosophy. Their whole cosmovision became worthless. So They didn't want to share this information. So what did the Pythagoreans do with Hippasos? Problem solved. So what do we learn from this? First, mathematicians can be really emotional, then they can be nasty people. And we also learn never trust your intuition or what you believe when it comes to mathematics. Only trust what mathematics says. And on a final note, it is important to know that the first people we consider to be mathematicians were also the first one to be betrayed by mathematics, and they will certainly not be the last ones. So let's go back to our main menu. Here we are. Now we'll see the green one. This is called the Treachery of Analysis. We see a trumpet, a horn, and the statement, "This is not the last judgment." So this geometric shape can be generated by this function f of x equals 1 over x if you imagine it revolving around the x-axis. So I think it is quite easy to see that you will obtain a similar shape to this one here. And here I would like to note, this geometric shape goes up to infinity on the right hand side, yes? So I couldn't do this in my artwork because I have a finite amount of space, but just keep in mind this goes up to infinity. It is an infinitely long trumpet. And the statement, "This is not the last judgment," connects to the name of this shape because it's called Gabriel's horn, because it looks similar to the horn that is announced in the Bible that will be used by the archangel Gabriel's horn, to announce the last judgment. So now we might ask, what is counterintuitive about Gabriel's horn? And it has to do with the volume and the surface area. So whenever we have a geometric shape, we can calculate the volume, in this case the volume of the region inside the horn, and the surface area. And it is amazing, but the volume will be finite, it will be equal to pi, and the surface area will be infinitely large. So we now may wonder, why is this counterintuitive? So let's imagine we take Gabriel's horn, this geometric shape, and we want to fill it with green paint. It will be absolutely possible. Why? Because we only need a finite amount of paint, pi units of the green paint, and we will finish the task. However, if we try to paint it from the outside, we will never finish, because we would need an infinite amount of paint, which we will not have, and because we'll never finish. And that is counterintuitive, because it seems that we would need more to fill the Gabriel's horn than to paint it from the outside. So there is an explanation to this counterintuitive result, and it's that paint particles are not infinitely small, and we cannot compare something that cannot be infinitely small with a geometric shape that will get infinitely small. So there is no way to compare these two experiences. So yeah, here we have the Treachery of Analysis. So we could say that Richard Dedekind was the first one to entirely fill in all the gaps of the real numbers, of the real line. And to better understand what I mean with this, it is a good moment to talk about how mathematicians work. So you probably heard that mathematicians prove theorems. But how do they do this? So a mathematician has a statement, he wants to show this statement is true, and he has two main tools. The first one is logic, reasoning, and the other one are other theorems that have already been proved. And of course, these theorems have been proved by the same way, by using logic and using other theorems that have been proved earlier. So the question that may arise is, where is the starting point? Because there cannot be an infinite chain of theorems. And of course there is a starting point. This starting point is called axioms. So axioms are the starting point of this way of working. Axioms are statements that we do not prove. So we accept them to be true and we use them to prove new theorems. So we could say that they are the starting point. And Richard Dedekind found a consistent way to start analysis in the real number. So he found the axioms of the real numbers. So it's quite amazing if you stop 1 minute and think of it, that we just saw that the Pythagoreans were the first one to discover there are not only rational numbers, but it took us more than 2000 years to entirely understand what this means. And it's thanks to Richard Dedekind, the mathematician who is not that well known by non-mathematicians, but who did a really important job. So let's go back to the main menu and see how we go on. So let's go for the orange one. The Treachery of Set theory. This was one of the classics. We see a pipe and we see the statement, "This is not a barber." The pipe is a reference to Bertrand Russell, a very famous philosopher and mathematician from Great Britain who was always spotted smoking a pipe. And the problem itself that this artwork refers to is Russell's paradox. It is a very important paradox in set theory, which has a version that is frequently used to explain it to non-mathematicians, and this is called the barber paradox. So let's see what this paradox is all about. Imagine a barber in a small village and he wants to make as much profit as possible. So he states, "I shave all those and only those who do not shave themselves." And if you think of it for a second, it seems to be quite a plausible thing to say. Why? Because all those men who do shave themselves, they won't go to the barber. So the barber focuses on all the other ones. And well, sounds plausible? It isn't. Why? Because there is one question that arises, and it's, who will shave the barber? So to better understand what's the problem, consider both alternatives. Either the barber does shave himself or he does not. There are no other alternatives. I think that's clear. And these two alternatives are mutually exclusive. So let's see what happens if we suppose that the barber does shave himself. If he does shave himself, then he belongs to the group of men the barber shaves. And how was this group defined? This group was defined as all men who do not shave themselves. So we started supposing that he does shave himself, and we conclude he does not shave himself. That does not make any sense. So let's go to the second alternative. He does not shave himself. And if so, then he belongs to the group of men the barber shaves. And if he belongs to the group the barber shaves, then it's because he shaves himself. So we see both alternatives lead to contradictory statements. And this is a huge problem. If you think of the other problems we considered, they were all confusing for us, but they were consistent within mathematics. It's just that we don't understand why they are true. However, here we have a result that is not consistent within mathematics, and that is a huge problem. We call such problems antinomies. And why are they so problematic? Let's see. So why are antinomies such a big problem? Well, the fact is that when you have an antinomy within a mathematical system, then the whole mathematical system becomes worthless. And this is a huge problem, of course. And why does it become worthless? Because you can prove whatever you want to prove by using this system. You can prove true statements, but you can also prove false statements, statements that are not true. And to show you this with a very little example, just imagine that 2 equals to 1, yes? I hope we all agree this is not true. And I state I can use this false statement to prove that I am the Pope, yes? So how do we do this? Well, imagine we have exactly two people in a room. One is Demian and the other one is the Pope Francis. Now, I say, if we have exactly 2 persons in a room and we have the 2 equals to 1, then we have exactly 1 person in the room. And since we all knew that in the room there was Demian and the Pope, we conclude Demian has to be the Pope, yes? And that's the proof. We used that 2 equals to 1 and we proved Demian is the Pope. From now on, I want you to call me Your Holiness. So here we have it, the treachery of set theory. And just so you can sleep at night, I can say this problem has been solved within mathematics, and it's quite reasonable, and I would like to share this with you. So going back to the barber said, I would like to shave all those who do not shave themselves. And here the mathematicians say, okay, you can do this, no problem. However, I want you to state and define the group of people you are considering for this task, for shaving. Who do you want to shave, so in general? And the answer could be, oh, well, I would like to shave men, because I always shaved men and only men. So another possibility would be, I would like to shave grown men, because I have never seen a kid enter this room. Another alternative, I would like to shave grown men who do not wish to grow a large beard. And this sounds reasonable to do. And why is this important? Because this whole statement then implies that in order for this not being a paradox, the barber cannot belong to that group. So if he says, I want to shave only men, it is necessary that the barber is no man, so that it's a woman. If he states, I would like to shave grown men, then it could be a woman or it could be a small kid. And if he stated, I will shave only those who are grown men who do not wish to grow a large beard. So in this case, it could be a grown man shaving with a large beard who does not wish to have a short beard. And yes, it sounds silly, but it's the mathematical way to solve this problem. Just the barber cannot belong to the group of people considered to be shaved. So this is the treachery of set theory. Let's go now for this one here, the treachery of infinity. We see a monkey and the statement, this is not a poet. So if we talk about counterintuitive results, it's impossible to get around infinity. Why? So I'm imagine that all of you understand what infinity means, so you have a basic notion. However, there is one problem. We have no experience with infinity. For instance, there is no infinity in school, nor in the park when you're playing football, nor are there scientific discoveries showing us infinity. We have no sense experience. There is no way we can have a feeling for what it means what infinity means, because we have no way to get an intuition for it. So let's see what problems can arise with infinity. This problem is called the infinite monkey theorem. We have a nice little monkey smiling at us, and we have a typewriter. And the problem says we allow the monkey to write stuff on the typewriter. What do we expect the monkey to write? Of course, some nonsense, gibberish. Why? Because it's a monkey, and he chooses the letters randomly. So we cannot expect this text to make any sense at all. However, what happens if we give the monkey some time? What if we give him eternity? So imagine our monkey won't die, the typewriter will work, he has an infinite amount of paper and ink and whatsoever, and the typewriter won't break. Is it possible that the monkey will write, for instance, the word mathematics? Well, now it seems quite a bit more reasonable, isn't it? And it's true. With probability 1, the monkey will have written sooner or later the word mathematics. But not only that, if we give the monkey enough time, an infinite amount of time, then it can be proved that sooner or later the monkey will have written down the whole written legacy of William Shakespeare. It's what we call the first folio, 1623, to be or not to be. And this seems quite amazing, but he will do it with probability 1. So there is 100% of chance that the monkey will write down the whole written legacy of William Shakespeare. and this is why he will become a poet. However, infinity is not a real concept, so this is not a poet. Here we have the two mathematicians most important in this theorem. Henri is the one who created the whole mathematical framework for probability. He is responsible for the axioms of probability, and Georg Cantor was the one who created a mathematical framework for infinity. So this was a very important, bold move. And there was a large controversy around this, and there were many mathematicians opposed to Cantor. However, time proved Cantor right. Why? Because now his work is the one we work with today, and we teach in our lectures to our students, and so it was not accepted back in the day, and today it's the only way we understand infinity. So let's go back, and now we go to the last one for today, and I choose this one, the apple, the treachery of geometry. This is not an apple, it's two. Here, one comment, this was actually inspired by another artwork by René Magritte, with the same sentence and statement, just that I added it's two. So what does it mean? First, before we start talking about the apple, something entirely different. So imagine we have a box with green marbles, and I ask you, can you take one marble out of it? What do you say? Well, let's check it out. No problem at all. If you have one box, it's no problem at all to take one marble out of it. Now, what if we have 4 boxes with different marbles? Is it possible to take one marble out of each and one of these boxes? And we can check it out, and we see this is no problem at all. We take one marble from each box. And I imagine that you believe me if I say, if we have many boxes, not just 4 but 1,000 boxes, if you give me enough time, I can take one marble out of each box. I hope you believe this. Yes, it's true. It's no problem at all. However, the question once again that may arise is, what happens if we have infinitely many boxes? So here we have it, infinitely many boxes with a lot of marbles, and can we take one marble from each and one of these boxes? So, does mathematics have answers to these questions? Well, yes and no, and yes and no. Let's see, what do I want to say with this? There was one guy, Ernst Zermelo, who said, sure, why not? If you give me infinite many boxes, I will take one of each and one of them. Of course, he was talking in mathematical terms, not in real terms, because we know we cannot have infinitely many boxes. However, there were others ones who said, no, this is Bauer, a very important mathematician who was against this. And so, yes, no, yes, no, yes, no. The gang sided behind Ernst Zermelo, and so now we say, yes, we can. And this is an axiom, the axiom of choice. So we do not prove this, we cannot prove this, but we work with it. And now let's go back to the apple and keep this in mind. So the theorem this artwork refers to is called the Banach-Tarski theorem. And since it's so counterintuitive, it's also called the Banach-Tarski paradox. What does it say? Well, it states you can take an apple. They talk about a three-dimensional ball, but let's talk about apples. You can take an apple, you can cut it 6 times, I think, but a finite amount of times, 6 or 7, and then take what you get from this, the slices, rearrange them, and when you're done, if you follow the instructions we give you, then you will obtain 2 apples of the exact same size as the original one. Of course, this is absolutely counterintuitive. That does not make any sense with reality, because it is impossible to take one apple do some stuff and get 2 apples out of it. It's nonsense. And here I wanted to try to make some animations with my presentation to show you this theorem, and I don't like it at all, but I left it to show you it's such an unreasonable thing to say that the visual representation was nonsense. Let's see. Zack. Boom. Slices. And then ta-da! 2 apples out of nowhere. This theorem does not make any sense at all in reality. I hope you understand what I try to say with this. So the reason why this is possible in the first place is because Banach and Tarski used the axiom of choice. So they do not cut the apple in a normal way, but they choose points of the apple, rearrange these points, and obtain 2 apples out of it. Of course I was not happy with this visual representation, so I created a comic. Here we have Banach and Tarski. This is Tarski, this is Banach, and they take a 3-dimensional ball, a solid ball. They use their knife, the axiom of choice, a magical knife with incredible sharpness, and as I said, they do not cut it in a traditional way, but rather create clouds of points. How do they create these points? With the axiom of choice. They choose different points of the apple and rearrange them, and of course we are not done because we have to rotate a bit, so we take a little bit of our sweet rotations, and poof, out of nowhere we have 2 solid balls. I'm quite more happy with this representation because it's more funny and it has a lot of how can I say it, references to history and philosophy of mathematics. It's quite fun, but yeah, that's another way of showing this result. So yeah, here we have it, the treachery of geometry. This is Ernst Zermelo, the guy with the axiom, a tremendous mathematician, and Stefan Banach and Alfred Tarski, 2 bosses of mathematics. And now we could argue, why on earth are we working with an axiom that creates such counterintuitive results, absurd results for reality? This has nothing to do with our world. This is 1 apple, it's not 2. But the thing is that this axiom is actually quite important. It is a very powerful tool, and it is fundamental to many branches in mathematics. I won't dive into this, but trust me, it is very important and it's very useful, and from this axiom we have many results that are super intuitive, and if we would work with this axiom we would get a whole bunch of other results which aren't intuitive either. So we work with it, I work with it, there are mathematicians who do not like it, I like it. So yeah, the treachery of mathematics, of geometry. So this is it for today. It's getting dark and winter is coming, so it's also getting colder. We haven't seen all of them. However, if you want to know what's behind each and one of them, just contact me, write me an email, or contact me on my social media accounts. I will write them down just now, right now. Until then, thank you very much for listening to me. You are amazing people, beautiful people. Stay safe, take care of each other in these strange times, and hope to see you soon. Just some remarks. The drawings you saw, I do them all myself. I like it very much to draw mathematicians. I write about mathematics and mathematicians. I also write in a science blog about mathematics. I do clothing, I design stuff, I created some games, and you all already saw the comic. So yeah, here you have it. If you want to contact me, you have my email, Facebook, Twitter and Instagram account. Hope to hear from you soon. Bye!